are nocturnal birds. As they fly, they produce a high-pitched clicking sound to locate obstacles using a pulse echo technique. Describe how oilbirds use a pulse echo technique to locate obstacles. So the idea is basically we've got a bird, whatever a bird looks like. This is what a bird looks like, isn't it? And it's got an obstacle. It sends out a sound and it listens for the echo. Okay, so the echo, they call it an echo, but we would call it a reflection. So what the birds are doing, the birds transmit clicks. They transmit clicks, and these reflect off the obstacles. Now this takes time, doesn't it? This takes time. The birds listen for or measure the time. Measure the time for the reflection to arrive. A big time means that the obstacle is further away. Okay, so the frequency of sound in an oilbird's click is 2 kHz, and a click is 2 milliseconds in duration. Determine whether these clicks can be used to locate obstacles at a distance of 50 centimetres. 5 marks. So we've got a click which is 2 milliseconds in duration. So the click, the pulse even, is 2 milliseconds in duration. So the question is, how far does the sound travel in 2 milliseconds? In 2.0 milliseconds, the sound will travel, S is equal to VT. So 330 times 2.0 times 10 to the minus 3. 330 times 2 times 10 to the minus 3 will travel 0.66 meters. So this is what I would call the length of the pulse. Now, one of the important things about the pulse echo technique, is that this pulse that you send out must not overlap with the next pulse, because you need to be able to distinguish, you need to be able to tell apart one pulse from the next pulse. So it sends out this pulse, which is 0.66 meters. So this must not overlap with the next pulse. So it's the distance is 50 centimeters, but that actually means the path is 100 centimeters or 1 meter. So it doesn't overlap. This must not overlap with the next path. The path is 1 meter, so this pulse will not overlap. So the pulse is suitable for measuring a 50 centimetre distance. Now the other piece of information they've given us is the frequency. Now with the frequency you can calculate the wavelength. Is going to be the speed of the wave divided by the frequency. So 330 divided by 2 diffraction. There is a limit. If the object is about the same, if you're sending waves at an object which is about the same as the wavelength, then you get a lot of diffraction of the wave on the way back, so it becomes very spread out. So the diffraction limit, one wavelength. So this is fine because 16 centimetres, that's 16 centimetres. 16 centimetres are fine. 17 centimetres isn't really 17 centimetres. 17 centimetres is fine because that distance is much smaller than this distance again. So there's no limit to resolution of birds flicking. So let me just find a bit of space in my box to write this. The wavelength is less than 50 centimetres, so the bird can resolve the obstacle. That's a little bit tricky, that last couple of marks, to get that answer, but you do need to say that this wavelength is important as well, because there's a limit. I think it's called the Rayleigh criterion, that you have a limit to the resolution. Explain why oilbirds emit pulses with shorter time intervals between them when they are close to an obstacle and when they are further from an obstacle. So this comes back to this argument here as well. Why does it make this time shorter when they are closer to an obstacle? So when they are closer, to an obstacle, the time for the reflection to return is shorter. The pulses must not overlap the bird must receive one pulse before transmitting another. So that means that they must have shorter pulses when they are closer. When they're closer together, the pulses must be shorter. So the pulse must be shorter for closer obstacles.